The inverse transform of arctan of 1 over s. All right. So, what do we do in this case? Well, so we're going to use the inverse form of the derivative of a transform. Okay, that is, it's 1 over t times the inverse transform of the derivative of the Laplace transform here. All right. Okay. So what are we going to do here? So we're going to do 1 over t uh, inverse transform of negative the derivative with respect s of arctan of s to the negative 1. This 1 over s, I'm going to move it as s to the negative 1 so we are able to differentiate. Okay, let's differentiate this using, of course, the arctangent rule. All right. Well, so let's see. So that is equals to 1 over t inverse transform of the negative, okay, careful with the sign, negative 1 over 1 plus the argument squared, that is s to the negative 1 squared, times the derivative of, what is that? The derivative of s to the negative 1, which is negative s to the negative 2, okay? Well, let me make this look like an S. There we go. Okay, let me group all these together. Okay, that equals 1 over t, right? 1 over t times the inverse transform of uh, negative times a negative. Isn't that positive? And that's actually going to be s to the negative 2 divided by 1, 1 plus s also to the negative 2. But hold on, we don't have inverse transform formulas for functions of s with negative exponent. Well, we're going to do a little trick here, a little potty trick here. So multiply and divide by s squared, essentially to, what's it called? Essentially to simplify the complex fractions together. So that is 1 over t inverse transform of 1 over s squared times 1, is that s squared, and s squared times s to the negative 2, is that a plus 1? All right. And what is that equal to? What's the inverse? What's the inverse transform of 1 over s squared plus 1? Well, on the formula sheet, it looks like it's a transform with the sign function, right? There's a constant. Well, there's a 1 squared and a 1. In this case, we don't need to compensate any factors, all right? Okay, so that equals sine t over t, all right? So that is our final answer. Okay. So the next topic in this section is about transforms of integrals, right? Well, in the second section in this chapter, we look at transforms of derivatives to solve differential equations. In this section, we did derivatives of transforms as one of the operational properties, you know? Okay, so what do we do in this case to find the Laplace transform of an integral from 0 to t of f of t dt without evaluating the integral, because these integrals may be given in a weird way, and also some of these integrals we may not even be able to evaluate. So, well, we have this form that is essentially 1 over s equals to f of s. So in other words, 1 over s times the Laplace transform of f of t. So what do we do? Find the Laplace transform of the integrand here, okay? And then whatever you get, multiply by 1 over s, all right? Okay, so what is this? Let's have actually, I'm not going to prove this result or this formula design because This derivation proof requires a little bit of real analysis, and that's way beyond the scope of our course. All right, so let's just go with it this time. Okay, so let's find the Laplace transform of the integral from 0 to t of e to the 2t cosine 3t dt. Okay. Well, so I mean, think about this integral right here. Remember that one from calculus 2? That's not a fun one to do. That's one of those that you have to treat it like an equation. And it may take at least a whole page. And also, this one has limits of integration. It's even more work. So, well, this is what we're going to do. We're going to multiply by 1 over s and find the Laplace transform of this function, e to the 2t cosine 3t. All right? Okay, have a look at that Laplace transform. Any idea? Does that remind you of anything? That's actually a combination. So in this problem, we're combining two theorems. Number one, the new Laplace transform of an integral in combination with first translation theorem. And again, it would be convenient to do 1 over s times the Laplace transform of cosine 3t. However, whatever we get evaluated at s equals to s minus 2. All right? Going to s minus 2. Okay, so transform of cosine of 3t, if you refer to the formula sheet, so that's the s over s squared plus k squared, okay? So let me go back to the notes. So that'll be equal to 1 over s. That's actually already s over s squared plus 9, whatever we get, evaluated at s minus 2. Okay? Hey, what happens here? Check. Here, be careful. I know what you might be thinking about this one. Yes, these s's cancel out, right? But no, do not cancel them out because this s right here will suffer a shifting here. All right? This 1 over s, it was not part of the transform that we are doing in the first place. So that came out of the integral theorem here. Okay? So this would be 1 over s, okay, times s minus 2. And that's a tricky part about this one. Be careful when you combine one like this. 1 over s minus 2 times s minus 2 squared plus 9. Final answer. Okay. And I mean, just to remind you, if you will, if it works for you. So we just, we don't touch the 1 over s. All right. Guys, if it works, this guy right here, this guy is untouchable. You can mess with that one, right? Like a powerful politician. Yes. Which one? To the duty world. That's what indicates the translation here using the first shifting theorem on the s-axis, right? All right. So here we go. Now let's do another one. The integral, the Laplace transform of the integral from 0 to t of t sine 4t. Okay, let's see what about that one. Actually, for this one, it's going to be another combination of two theorems. Because do you see this multiplication by t? Well, that's going to be the derivative of a transform. But first of all, let's apply this integral theorem, the Laplace of an integral. That is 1 over s. This is untouchable again, right? Find the Laplace of t sine 4t. Okay. All right. Well, now forget about the 1 over s. Forget about the integral. Focus primarily on taking the Laplace of t sine 4t. Well, t. Well, in this case, that looks hell lot like what we did at the beginning, right? -1 to the end derivative of the Laplace transform. In this case, since the power of n, okay, how did we do this? Remember how did we do this one? N equals to 1, all right? and f of t equals to sine 4t. So what do we have? Yes. Which one? The power of the t right here. Okay. So what else? Okay, yes. So this will be 1 over s, okay, times negative dds, the derivative with respect s, of the transform of sine 4t. Okay. All right. So this will be equal to 1 over s. And the transform of sine 4t, is that the one with the 4 in the numerator, the constant in the numerator, and quadratics in the denominator, plus 4. All right. Actually, this is supposed to be negative, isn't it? So here, don't forget to carry that negative. And, oh, wait, but we still, hold on, we still need to differentiate this guy. Negative BDS, 4 over s squared plus 4. Well, let's differentiate this one. We did something like this before, remember? So this will be 1 over s times negative the derivative with respect s. I'm going to rewrite this in a more convenient form. S squared plus 4 to the negative 1. Okay. And use a mini chain rule here. Okay. So this is 1 over s. Actually, I'm going, negative 1 times negative. Doesn't that become positive now? So this would be 4 times s squared plus 4 to the negative 2 times 2s. Okay. And simplifying all this, we get, actually, in this case, we may go ahead and divide out these s's because those s's are not going to go through a shifting like before. All right. Yes. Hmm. Yes. So this one is supposed to be a 16. Thank you. It's the square of it, right? Thank you. Yeah. All right. So let's simplify. Let's keep simplify. 4 times 2. That equals to 4s. No, 8 rather. Divided by s squared plus 16 quantity squared. Final answer. All right. So this is what will be doing throughout this section. Combine more than one rule, Um, so let's see. Let's have a look at another property, another form. Okay, so now we're going to find the integral of a transform rather than the transform of an integral, which in this case it's a division by t. Remember the derivative of a transform was a multiplication by t? What's the inverse of the derivative integration? So if back then we multiplied by t, the inverse makes sense to divide by t. All right. Okay. So if we wanted to evaluate the Laplace transform of some function rather than being multiplied by t, but in this case divided by t, all we need to do instead is to integrate between s and infinity the Laplace transform of the function without the dividing by t. Because finding the Laplace transform of a function over t may not be an easy task. Okay, this one I'm going to show you how that works. So let me start with the integral from s to infinity of the Laplace transform of f of t. Okay, ds. All right. Okay, guys, by definition, what's the Laplace transform of t? Okay, isn't that another integral? So this will become a double integral from s to infinity. And then let me actually highlight. Oh, no, no, not all of it, just this part here. Okay, this will be the integral from 0 to infinity of e to the negative st f of t dt, and then let me bring back the ds. All right. So that actually becomes the what we call the theorem. Okay. If we wanted to keep moving on from here, we have a little problem. Well, because we can't integrate with respect to t because we don't know what this function of t is, do we? We don't know what it is. However, remember Calc 3, Fubini's theorem, when we can interchange the order of integration provided the limits are constants. We can do that. I mean, S, yes, I know S is a variable technically, but well, let's think of it as a constant. It's a number in the new domain in S. I'm going to interchange the order of integration here and 0 to infinity and S to infinity and the same integrand e to the negative st f of t ds dt. Okay, do you guys agree that we can integrate with respect s, because this function of t is a constant, and then the integral of the exponential, okay, check this out, the integral from 0 to infinity of itself e to the negative st times f of t. However, isn't that the by 1 over t, actually negative 1 over t, all right? So this is, this would be evaluated between 0 and infinity. And don't forget the dt. Okay? So let's focus on fundamental theorem of calculus for the, what's it called? For the um, for what you just got here. Okay, so this would be negative 1 over t. I'm going to open brackets. For upper limit of integration, I have to set a limit because that's an improper integral. So that'll be the limit as, what is that? B approaches, or rather S approaches infinity of e to the negative st, okay, and minus the lower limit of integration right here, which will be e to the negative st. That's still okay. And don't forget to multiply by f of t dt. Okay. Well, so what is going to happen here? What happens at the upper limit minus lower limit? Okay. So where is this limit going to go to? Isn't that limit going to go to 0? Okay. That's going to go to 0 for s equals infinity. Okay. And I know you might argue, okay, we need to multiply this by the function of t, but actually the function of t is going to grow slower than that exponential in the denominator. And that's also part of the Laplace transform condition, that any function is of exponential order. That is, the exponential will always dominate any other function. All right. Okay, so what is that going to leave us with? This is going to leave us with the following. Okay, negative times a negative, isn't that equal to positive? This is equal to the integral from 0 to infinity of e to the s negative st over t times f of t dt. I'm going to regroup this. This is the integral from 0 to infinity of e to the negative st times f of t over t dt. Isn't that the definition of the Laplace transform for f of t over t? Okay, that's Laplace of f of t over t. And that's the end of the proof. All right? It all goes back to the improper integral. That's it. Right? And do a couple of manipulations here and there. That's all it is. Okay, well, let's see about this one. Let's have a look at one example. Find the Laplace transform of sine t over t. Let's see what we get about this one. Okay, by this theorem, let me actually write it down at the top. The integral from 0 to infinity of Laplace of f of t dt equals to Laplace of f of t over t. Actually, I should have written it the other way around, all right? Because we're going to start with a form like the right-hand side. Okay, guys, so this is the same as saying instead, evaluate the integral from s to infinity of the function f of t, which in this case is simply sine t. Oh, wait, Laplace sine t ds. All right. That's all we're going to do here. All right. Number one, what's the integral? I mean, what's the Laplace transform of sine? Isn't that 1 over s squared plus 1 ds? Okay. Okay, let's integrate this one. Isn't that just the arctangent rule? Is that the arctangent rule? That equals arctan of s evaluated between s and infinity. I know it's kind of weird to see the same variable s on the limit and as a variable. That's all right. That's fine. Okay, so for the upper limit at infinity, I need to set up a limit. Limit as b approaches infinity, or rather as s, not b, as s approaches infinity of arctan of s minus arctan. I'm going to put brackets because this limit symbol only is accountable for the arctangent of s, not for the arctangent of this. Yes, this is another s, okay? Arctan arctan s. Well, you know what? Let me do the following so you don't get confused with too many s's. Let me change this to a b, change that to a b, so you don't get confused with the letter. Let's keep the usual thing we do in Calc 2 for improper integrals. All right? Okay, so where is this limit going to go to? Arctan of infinity. What is it? Pi over 2. Pi over 2. And arctan of S is simply arctan of S. Okay, so this is pi over 2 minus arctan of S. Final answer. Okay. We're going to do the same for another example, for another function of t with a division by t. That is 1 over cosine of t divided by t. Let's see what we get about it. All right. So number one, the Laplace transform of a function divided by t to the first power, it's the same as evaluating the integral from s to infinity of the transform of the function in the numerator. That is 1 minus cosine t. Okay, ds. All right, let me actually highlight it so you can relate it to it, you know. So 1 cosine, just like here. Okay, that's how. Okay, let's forget about the division and integrate. Well, let's take the transform of the integrand here. That is the integrand, the integral from s to infinity of the Laplace transform of just the number one. Isn't that just 1 over s? And the transform of cosine, that's minus s over s squared plus 1 ds. All right? Let's split it into two integrals to make this easier. Okay, so, or even better, no, that's fine. Let me do it in two integrals. That is the integral of 1 over s from s to infinity with respect s minus the integral of s over s squared plus 1 ds from s to infinity. Well, so the first integral and rule, no problem. What about the second integral? Any ideas how to evaluate that second integral? Another ln rule. However, when we see the differential, we wished we had 2s here, right? We can make our wish come true again, provided you divide one out, right? Multiply by a half outside. That's how we compensate our differentials. So what is it going to be? Uh, this would be equal to ln of s minus 1 half ln of s squared plus 1 evaluated between s and infinity. Okay? All right, guys. Upper limit, which is infinity, minus lower limit, which is just the variable s. We can't just evaluate at infinity like that. I'm going to set a limit for this one, first of all. All right? Also, uh, yeah, about this one right here. Okay, guys, the what I'm gonna do here may be a little weird, but it's something we need to get used to. So, and in the end, this all lands on the fact that we can make our wishes come true. You know, just like we wish we had a two right here, We can make it happen, multiply, provided you multiply with the reciprocal outside. That is essentially do the reverse or the inverse operation that we do. Okay, do you guys agree that ln of s is the same as saying ln of s squared times 1/2? Would you guys follow that? That's because if we smack down the 2 to the front, that's essentially a 2 over 2, which is still a 1. And you may wonder, but why do we want that in that format? You will see in a second. You will see this in a second, okay? So, number one, let me set up the limit. Let me rewrite and set up the limit. So what I'm going to do here is limit, wait, limit as b approaches infinity of ln of b, but actually I'm going to make it 1/2 and squared here, okay? I'll show you why in a second. Hold on, okay? Minus 1/2 ln of, what is that? B squared plus 1, okay? So this is a limit at infinity minus the lower limit. I'm going to go back to the variable s minus, and I'm going to do the same trick. 1/2 ln of s squared minus 1/2 ln of s squared plus 1. All right? Okay, guys, the reason why I'm doing this party trick with logarithms, it's because if we evaluate this limit, what's natural log of infinity? Isn't that going to go to infinity minus another infinity? What is infinity over infinity? It's not zero, right? Because we don't know which infinity is bigger than the other one, so they don't necessarily cancel out. So the reason why we want to do this is because I'm going to write this as a quotient of two logarithms. Number one, I'm going to factor out the 1/2 that equals 1/2 the limit as b approaches infinity, and this will be ln of b squared over b squared plus 1, and then minus same 1/2 ln, okay, minus ln of s squared over s squared plus 1. Okay, so now what is that limit equal to? Right here. Where does that limit go? Okay, number one, when doing in the argument, okay, it's going to go to 0. However, evaluating polynomial over polynomial inside of the logarithm, the degrees match, all right? And that's 1 over 1. So the limit would be 1. But what's the natural log of 1? 0. That's why. If we kept it the other way around, we would have gotten a logarithm of 0. So check. Let me do that on the side real quick. If I didn't do this party trick with the logarithms, I would have gotten the following. Something like ln of b over 1/2. Wait, no. Of ln of b, something like ln of b divided, okay, b by the square root, by ln of the square root of b squared plus 1. That would have been a bit harder to evaluate, right? That would have been a bit funky to evaluate. So that's why I did this trick right here, okay? Okay, let me go back and finish. Oh, so final answer, that's simply this result. Negative 1/2 ln s squared over s squared plus 1. Now, if you don't like the negative sign in the front, that's no problem. Get rid of the negative, s squared plus 1 divided by s squared. Either way, okay? Okay, so at this point we have covered the majority of the theorems of the forms for finding transforms, transforms for most functions. Okay, so the next topic in this same section before wrapping up is using multiple theorems in one single one. Yes, I forgot the 1/2. Yeah, I don't know what happened. Okay, thank you. Good call. All right, so let's evaluate the Laplace transform of t e to the 3t sine 2t. How do we evaluate this one? Imagine trying to evaluate this using the integral from 0 to infinity of e to the negative st, t e to the 3t sine 2t. Can you think of the integration by parts this would take? I don't want to do this using the integral. Well, we're going to take advantage of all the theorems that we have over here. Okay, so to begin with, one that comes to my mind, the minute you see an exponential factor, what does that make you think of? First translation theorem, right? Which is on your formula sheet, essentially, that is, I should have numbered instead of bullets here, okay? I'm going to update it to make it easier, okay? So it's, where is it? Oh, this one right here. Whatever Laplace transform of the function shifted s minus a units, okay? So first, let me set it up with the proper notation so we can easily follow what we do. That is t sine 2t evaluated at s equals to s minus 3 in this case, right? Forget about that translation. We're going to take care of that one at the very end. Focus on what's inside the curly braces. T sine 2t. What is that? The derivative one, right? The multiplication by 3, right? So multiplication by 3, okay? I mean multiplication by t. Multiplication by t, okay? What does that ask us to do? To find the negative 1 to the n times the nth derivative, in this case, because n equals to 1, with n equals to 1, that is negative the derivative, all right? Negative the derivative with respect s of the Laplace transform of sine 2t, whatever we get, don't forget about the shifting to s minus 3, all right? Here we go. Okay, the Laplace transform of sine 2t. At this point, so negative dds times 2 divided by s squared plus 4. Okay, yeah, whatever we get, s to s minus 3. Let's evaluate the derivative first, and then we do the shifting at the very end. Okay, the shifting is saved to the very end. All right. Side note, yes. Let me do that as a side note. Shifting. Okay, first, shifting theorem do at the very end. All right, we do it at the very end. All right, once we have found the derivative and all that. All right, okay. And the reason why is because you don't want to end up with a huge polynomial and do a big derivative. No, you don't want to do that. You don't want to do that. Okay, so the derivative again, that's negative. The derivative with respect s of 2 times s squared plus 4 to the negative 1, whatever we get, s minus 3. Okay, and then this is negative dds. Find, oh, wait, no more dds because I'm going to find the derivative. Okay, negative times negative 2, s squared plus 4 to the negative 2 power times 2s. Whatever we get, s goes to s minus 3. All right? The rest of the problem, simplify, and then shift s's to s minus 3. That's it. Okay, so what is it? Negative times a negative, is that positive? And then 2 times 2, is that 4s over s squared plus 4 quantity squared, where s goes to s minus 3. And finally shift. 4 times, okay, let me actually highlight and indicate the shifting finally goes here and there. Okay, so that is 4 times s minus 3 divided by s minus 3 squared plus 4 quantity squared. Final answer, right? Right. Hmm. More exercises where we will put together a few of these theorems. And well, of course, you're going to take a few for practice later. Okay, so what about the next one? The next one, okay. Okay, yes, that oh, this one is a good one. Okay. The Laplace transform of t times the integral from 0 to t of sine t over t dt. What? No, we can't cancel those t, the t in front of the integral and the t in the denominator. We can't do that, right? So we're going to focus on doing the theorem. So number one, what about the first c right here? What does that actually remind us of? The derivative, right? Okay, so forget t provided you differentiate. Okay, so negative dds times the Laplace transform of the integral from 0 to t of sine t over t dt. Okay, how is that? Because by multiplication by t. What is that? What is that? On the formula sheet, that's actually the the derivative of a transform here. Yeah, I should have numbered them again. Okay, anyway. So what is that? What's next? Okay, so what about, okay, now the next theorem. We want to find the Laplace transform of an integral of a function that at the same time is divided by t. Wait. What do we do first? Well, the first operation we see, it's the integral, don't we? So we're going to go with the derivative of the Laplace transform of an integral. That is this formula right here, transform of an integral, which tells us to do 1 over s times the Laplace transform of the function we have in the integrand. All right? Okay. That means equals to, that equals to negative dds, keep it, times 1 over s times the Laplace transform of sine t over t. Okay? But guys, didn't we already do the Laplace transform of sine t over t? Didn't we do that already? What was that? Okay, actually, let me use, how about we just use that result, you know? So, wasn't that pi over 2 arctan of s minus arctan of s? Let's just use it. Okay, let's just use that result from before. I mean, I don't want to compute everything. So, this will be equal to negative dds of 1 over s times, okay, pi over 2 minus arctan of s. All right? All right, so we need to differentiate this. Well, let me simplify this a little bit. I'm going to distribute the s. And at the same time, since we're going to differentiate that 1 over s after distributing, I'm going to move it to the numerator with negative exponent. So negative dds of pi over 2 s to the negative 1 minus s to the negative 1 arctan of s. Okay? Well, let's find the derivative as if we were in Calc 1, you know? Why not? So that is negative, no more derivative symbol because we're already differentiating. Negative 1 pi over 2 s to the negative 2 minus, did you guys agree that we product rule s to the negative 1 times arctan of s requires a product rule to be differentiated? Okay, so the derivative of s to the negative 1, that's negative s to the negative 2 times arctan of s, plus the derivative of arctan of s, which is 1 over s squared plus 1 times s to the negative 1. Okay? there's going to be a lot of negative here and there going on. So how do we do this? Okay, so I'm going to write everything in terms of positive exponents at this point. We're essentially done, you know? So number one, negative pi over 2 s squared minus, actually, let me do minus minus that equals to plus arctan of s over s squared, and then minus plus, it's another minus. That's simply s to the negative 1, that's s times s squared plus 1, divided, I mean, in the denominator of 1. The last step right here is just to distribute the negatives, right? That's pi over 2 s squared minus arctan of s over s squared, and then, oh wait, yeah, and then plus 1 over s times s squared plus 1. And that's final answer. Okay, that is our final answer. Okay, one more, and we move on to the next topic. Okay, what about the Laplace transform of e to the 3t times the integral from 0 to t and from of t sinh of 2t dt? Oh, what is this? So first thing we see, reading the expression from left to right, what is it? Translation, right? The exponential e to the 3t indicates a translation along the s-axis, which is something we're going to leave for the very end. All right. Well, so what are we going to do? So that is the Laplace transform of the integral from 0 to t of t sinh 2t dt. Okay. And well, this should be evaluated at s equals to s minus 3. All right. What's next here? So, well, the Laplace transform of an integral. How do we transform an integral? Okay, formula sheet. The Laplace transform of an integral is the third to the last formula, that is 1 over s times the Laplace transform of the other function, that it's not t, okay? So, what is this? So, this will be, I'm going to take that 1 over s, okay? 1 over s, wait. No, no, no. What am I doing? Oh, no, that's fine. Laplace transform, okay, of t sinh 2t. All right, no more integrals, but a 1 over s. But don't forget that we are still translating this or shifting to s minus 3. All right, what's next? Take the transform of t sinh 2t. What about that t? What about that t? What is that? Derivative, right? First order derivative. Luckily, we're not doing second order derivative. Otherwise, it's going to be madness. All right. So this will be number one, 1 over s, okay, times negative the derivative with respect s of the Laplace transform of sinh 2t. And whatever we get, shift it to s minus 3. All right. You guys following me here so far, so good? I know it's a lot going on, but I mean, it's putting everything together essentially. Okay, finally, let's find the Laplace transform of sinh. It's just like the sine function, except with a negative sign in the denominator. That's all it is. And if you want to verify that, well, refer to the formula sheet. Okay? Sinh k over s squared minus k squared. All right, let's go. So that equals 1 over s negative the derivative with respect s of 2 over s squared minus 4. whatever we get, shifted at s equals to s minus 3. All right. Again, no quotient rule. Move it to the numerator and chain rule. I'm gonna take that negative out. Well, no, keep it there. Actually, 1/s negative the derivative with respect s of 2 times s squared minus 4 to the negative 1. Whatever we get, s to s minus 3. Okay, differentiate that using the chain rule. That's negative 2. Okay, that equals negative 2 times the negative. Okay, that's 1/s. No more derivative symbol. I'm just going to write this in positive 2s squared minus 4 to the negative 2 times 2s. Okay, and don't forget to keep shifting. S going to s minus 3. All right, we're done essentially. Let's just simplify this and do the shifting at the very end. Okay, so what about um that is 4, okay, 1/s times 4s over s squared plus or minus 4 squared, and that's it, right? And shift it to s minus 3. Well, in this case, we can actually divide out the s's, and that's 4 over s minus 3 squared. Wait, yeah, squared minus 4 quantity squared. All right. Yes.
Why did it cancel out in this situation?
Oh no, it was an untouchable one, right? Wait. Oh no, no, no. It's not this. Okay, in this case, it's not untouchable because we didn't do that in the very beginning. That's the reason why. All right. It's not untouchable. This one is, yeah, this one is touchable. Yeah. Okay. So let's see. Let's talk about periodic functions. Okay, let's define what a periodic function is. A function f of t is said to be periodic if there exists a positive number t such that f evaluated at t plus t gives us back the function f of t. I mean, I think you guys know the one of the simplest functions, sine or cosine, with a period of 2 pi, whose angles are coterminal to 2 pi. I think that's the best example, right? Okay. And in this case, for all x in the domain of f of t, and t is the period. Okay. Again, like in the sine or cosine function, the period is 2 pi. All right. But what if we add more periods and more periods and more periods, repetitions of periods? Okay, check this out. So, for instance, f t plus 2t, that's the same as saying f of, okay, t plus t, all right, plus t. Do you guys agree that t plus t equals to 2t? Okay. Well, using the definition of a periodic function, this is equal to f of t plus t, which at the same time is f of t. You know, I mean, it's like adding, it's like having the function sine t, right? You can add, you can evaluate f of sine of t plus 2 pi, right? Or f of, what is that? F of, no, sine of t plus 4 pi, which at the same time is sine of t plus 2 pi plus 2 pi. And then all multiples of 2 pi, right? Well, that essentially takes us back to the original function, all right, because of the period. And same, inductively, f of 3t, f of t, I mean, f of t plus 3t would be back to f of t. So in general, if we add n multiples of the period, that's the same as going back to the original, to the value of the original function for all n in the integers here, all right? Not just any real number, just for integers. Okay. In addition, the smallest positive value of t that satisfies the condition of periodicity, it's called the fundamental period. We're going to talk about that fundamental period. I'm going to show you how we're going to get that fundamental period from some exercise, from some examples here. Actually, that's what, speaking of such, that's what we have. Okay, have a look at this function represented by the graph below. write it as a periodic function and state its fundamental period. Okay, so this function looks like all a bunch of diagonal lines interrupted every how many units, every unit, right? So the shape of the graph repeats and repeats and repeats every unit. Okay, so well, actually, if we think about, there is one unit every time the graph repeats itself. That is the fundamental theorem, the fundamental period. I mean, okay. But what is it, guys? Okay, what is the what? How do we represent this function? Isn't that just a diagonal line? F of t equals to t, like y equals to x. Okay, so this is f of t equals to t. However, with the condition, okay, with the condition that zero starts at zero and finishes at 1. Technically, we should have open circles here just to be more specific, but the graph didn't do that. Okay, let's just do that by hand. Okay, so 0 to 1 repeats, 1 to 2 repeats, 2 to 3 repeats, it repeats and repeats. So the question here is, what is the fundamental theorem, the fundamental period? Okay, fundamental period would be t equals to 1 because the graph repeats itself every 1 unit. All right. So this means, for instance, that f of t plus 1 would be f of t. All right. You guys agree with this? Even better. If you're not convinced of this, okay, check this out. Um, okay, how about we define the function in a different way? Check this out. Rather than defining the function f of t as equal to t, how about let me do it with the second diagonal line. Okay, isn't that the function t minus 1? Okay, but in this case, it goes between 1 and 2. All right. And well, what's the period? The fundamental period, it's still the same. I mean, evaluate what is f of 1/2? Isn't that 1/2? All right. F of 1/2 equals to 1/2. What would be f of 3/2? Isn't that the same as saying f of 1/2 plus 1? But guys, f of 1 f of 1/2 plus 1, well, I mean, the 1 is a period, isn't it? It's a fundamental period. That's the same as saying f of 1/2, which is another 1/2. Okay, go to 3/2 in this case. What's the y value? 3/2. Is that the same 1/2? Okay, you can add one more unit and add one more unit, and you should get the same result. Let's have a look at another example. These are going to get fancier, okay? Analyze the function represented by the graph below. Okay, we have a bunch of horizontal lines interrupted with jump discontinuities here and there. Okay, well, let's see about it. Okay, so you can determine the fundamental period anywhere you want. I mean, it's going to be true for the entire domain of the function. However, I like starting at 0 and see how the shape of the graph repeats. That doesn't always work. That's actually the next example. Okay, for instance, here. Did you guys agree that the shape that repeats for this function is this guy right here? And then you see it again like this, and then again and again. Okay, so what happens? So we have the function. Okay, let's describe this as a function, as a piecewise function this time, because this time we have more than one shape essentially. F of t, that is 1 for t going in between 0 and 1. Actually, let me put open circles at the very end. Okay. And it takes the value of 2 between 1 and 2. Do you guys agree with this piecewise function? For And I mean, do I really need to say that it's 3 for 2 and 3? Do I really need to do that? We don't need in this. I mean, if you want, that's fine, but you don't need because that actually okay. This set of functions in the piecewise function comprises the actual periodic function. The it actually it relates to the fundamental period. Which, by the way, what's the fundamental period for this one? How many units? That's 2 units this time, right? So you go right here and then repeat every 2 units, every 2 units. Okay. It's like doing different cycles for a sine or a cosine function. But in this case, we're not dealing with those functions. We're dealing with other piecewise functions here. Okay. So fundamental period t that equals the 2. All right. Okay. So what do we have? Hmm? One more. About that function. Okay. Analyze the function represented by the graph. So write it as a periodic function and state its fundamental period. Well, this time it's not the what I was mentioning before that starting exactly at 0, it's not going to work because do you see the shape of the graph? It's parabolas shifted to the right and to the left, but actually what I would like to think of the fundamental one, it's actually that is the one that's symmetric about the y-axis, right? The one in the very middle. So I'm going to look for the fundamental period in here. How many units? 4 units this time, right? The period equals to 4. Okay, how do we represent that function? Does that look like a function you're familiar with? Which function is it? Or f of t, in terms of t, equals to t squared. Condition, yeah, this is not just f of t equals to t squared. Otherwise, it would be going forever like this, which is what we don't have. This is a repeated function, a periodic function. This goes from -2 to 2, right? Or between 2 and what would be next? 6, or between 6 and 10, or between 10 and 14. See what I'm saying? Either way. But actually, we describe it in these terms because we look at in the interval where we have the smallest value possible. All right? Okay. The fun part. The fun part. How do we find the Laplace transform of a piecewise function like this, of a periodic function? Well, that's the formula. And guess what? I'm going to derive this formula. It's a fun one to do because it connects a bunch of stuff from calculus 2 as well, from sequences and series as well. You'll see. Okay, so if f of t is piecewise continuous on 0 to infinity and of exponential order, I mean the two conditions for the existence of the Laplace transform, and periodic with t, the transform of such a function would be 1 over 1 minus e to the negative st times the integral from 0 to t e to the negative st f of t. Okay, let me derive this formula. Okay, guys. So, do you guys agree that the Laplace transform of the function f of t, what's the definition? That's the integral from 0 to infinity of e to the, well, actually, no, yeah. Okay, 0 to infinity of e to the negative st, f of t, dt. Okay? I'm going to need to make more space. Yeah, I'm going to have space here. I'm going to do it here. Because guess what, guys? A piecewise continuous function that has a period t. We're going to chop this, we're going to chop this function. How? Well, we can go from 0 to infinity, making as many stops as we can. Those stops are going to be in the form of jump discontinuities potentially. Well, so this means our first stop, okay, that's the integral from 0 to t, okay, of e to the negative st, f of t dt, plus second stop from t to 2t of e to the negative st, f of t dt, the all lowercase. Okay, and let me do just one more. Third stop from 2t to 3t e to the negative st f of t dt plus infinitely many terms, all right? Because we're going to infinity. We're going all the way to infinity. Okay, so we need to talk about these limits of integration. I would like to make a substitution here. Okay, so I'm gonna make the subst for the okay, so for the second integral right here, I'm gonna make u equals to t minus t. I mean, a lowercase t minus uppercase t. Okay, so that means t equals u plus t. On the other hand, for the third integral, I'm going to make this substitution u equals to t minus 2 uppercase t, which means t equals to u plus 2 uppercase t, which represent the period. All right. So let me continue with the substitutions in the next step. So the first integral, guys, remains the same, no problem. Okay, that equals, wait, change blue. That is what? Okay. The integral from 0 to infinity of f of t. No, 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 0 to infinity, from 0 to t, the first stop. F of t e to the negative st dt plus the integral from 0 to t, uppercase t, all right? From 0 to uppercase t of, what is that? F of u e to the negative s times t, which is u plus t dt. Actually, this would be du, right? Plus the integral from 0 to t still, because I'm shifting everything to t actually. Okay, it's going to be the same. It's going to be, you guys agree that t, 2t, 3t, 5t, 157 million t is equal to t because that's the fundamental period. So we can use the same upper limit of integration. And guys, it will be convenient for the following reason. You'll see. So f of u equals e to the negative s u plus 2t, okay, du plus dot dot dot, okay? So time to do some magic here. Okay, so the first term, the first integral, 0 to t, f of t, e to the negative st dt, plus the integral from 0 to t, f of u, e to the negative s, u, e to the negative st, du, okay? And what else? Uh, Plus the integral from 0 to t of f of u e to the negative su e to the negative 2st du. Then a third integral with the same, with the last exponential factor e to the negative 3st and e to the negative 4t, 4st, etc., etc. You guys follow the pattern? So I'm just going to write two of them. All right, I want to write too many, but I'm going to just write two later. Okay. All right. So because we're integrating, guys, with respect to u, do you guys agree that e to the negative 2st and e to the negative st, those are constants that we can take out of the integrals? I'm going to do that. The integral from 0 to t, f of t, e to the negative st, dt plus e to the negative st, uppercase t, by the way, integral from 0 to uppercase t, f of u, e to the negative su, du, plus what is that, e to the plus e to the negative 2st integral from 0 to t f of u e to the negative su du plus dot dot dot, infinite in many terms. Okay, guys, what's next? So how about from here, let's okay, what did I do here? Okay, you guys, okay, did I did a change of variables from the world of t to the world of u? But guys, that would be essentially a definite integral, which would give us a numerical result. And how do we get there? I mean, by how do we get there? I mean, doesn't matter what dummy variable do you use. We can use u. We could have used v, or I'm gonna write this back in terms of t. Integral from 0 to t of f of t e to the negative st plus e to the negative st, integral from 0 to t f of t e to the negative st dt plus e to the negative 2st, e to the negative 2st e to the integral from 0 to t f of t e to the negative lowercase t dt plus dot 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 many terms. Why did I do that? Yes.
E, um,
Oh, I forgot the dt here, right?
the T and the exponential, the second exponential, is it?
Upper uppercase. No, you're right. This is uppercase T. Thank you. Thank you. That matters. Okay. So guys, the reason why I'm doing this, it's because check this integral right here. That integral. Do you guys agree that the integral is a common factor? I'm gonna factor it out. Okay. So I'm gonna factor out the integral. That is the integral. Leave some space for something. Okay, let me actually leave even more space. Integral from 0 to t f of t e to the negative st dt. Okay, let me open parentheses. Did you see the invisible one factor here? Okay, write it down inside of the parentheses. 1 plus e to the negative st plus e to the negative 2st, and inductively e to the negative 3st plus dot 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 infinitely many terms. Do you guys recognize the sequence or the series rather in parentheses? What is it? Check this out. This looks a lot like sigma n equals 0 to infinity of e to the negative st to the n power, isn't it? It's a geometric series, isn't it? Okay, so that is times the integral from 0 to t of f of t e to the negative st dt. Hey, but how do we evaluate such an infinite sum? Recall that there are two possible outcomes for this geometric series. Diverges for the common ratio equal to 1 or greater, but converges if e to the negative st is less than 1. Remember? That's the common ratio. Okay? And in the because we want this to converge, of course, we don't care about anything that diverges. So let me recall. So but E sigma n equals 0 to infinity of r to the n equals 1 over 1 minus r, provided r converges, or rather the absolute value of the common ratio is less than 1, which is our assumption here, all right? Which is what we want. We want convergence, I mean. Okay, so what does that mean? This will be 1 over 1 minus r. This guy right here equals to r e to negative s t times the integral from 0 to t f of t e to the negative st dt. And that's the end of the proof. That's how. Right? Again, guys, you're not responsible for memorizing these proofs, for knowing these proofs for the exam. It's just that I like to show where things coming from rather than just giving formulas away. Actually, it's pretty cool connections with stuff from calculus. That's why I like doing all this. Okay, let's find the Laplace transform of what is that? Of this function represented by this up down up down. Okay, one example, we're done. Okay, so number one, fundamental period for this one. After how many units do you see the shape of the graph repeat itself? How many units? 2 units. So we have a period of 2. t equals to 2. Okay? So as a piecewise function, f of t equals to 1 and 0. 1 if t is in between 0 and 1, and 0 if t is in between 1 and 2. Again, open circle, open circle, open circle, open circle.
Okay.
Okay, so let's find the transform of f of t. So what do we do? So Laplace of f of t equals 1 over 1 minus e to the negative st, integral from 0 to t of the fundamental period f of t e to the negative st dt. Okay? So, wait. This t is uppercase t for the period. Okay? Substitute. Substitute. Okay, so this is equal to 1 over 1 minus e to the negative 2s times the integral from 0 to 2. Okay. Oh, wait. I wouldn't be able to do the integral from 0 to 2 because this is a piecewise function, right? So this should be number 1. Check this out. The integral from 0 to 1 plus the integral from 1 to 2. All right. That's how we're going to break this problem up. E to the negative st times 1 dt e to the negative st times 0 dt. Yes.
Would it be an improper angle? Because the circle, the open circle.
Um, Technically, but let's leave it like this. You're right. No, you're right. You're right. But let's just leave it like this. So the value of this integral right here goes to 0, right? Because the integral of 0 times something, that's the integral of 0, so that's 0. The integral here, okay, that equals 1 over 1 minus e to the negative 2s. Well, that is the integral of e to the negative st with respect to t is that negative 1 over s e to the negative st from 0 to 1, okay? Which is, what is that equal to? That equals to 1 over 1 minus e to the negative 2s. And let me save this. No, that's fine. Let me open bracket 1 over s, technically negative 1 over s. And again, the dummy variable here, the limits of integration go only for the variable s. I mean, for the variable t, not the variable s. Okay, so this will be 1 over negative 1 over s times e to the negative s times 1 minus e to the negative s times 0. All right, and then simplify. We're almost done. Well-ish, actually. 1 minus e to the negative 2s times negative 1 over s. And what's the result? E to the negative s minus 1. Negative s 1 minus 1. What do we do here? What do we do? Okay. Simplify this algebraically. Okay, actually, check this out. What did I do in my notes? Well, I'm just going to use this negative here. Okay, so 1 over 1 minus e to the negative 2s times 1 minus e to the negative s divided by s. You guys agree with this? Negative, reverse the order, division by s. Okay? And then I'm going to group everything in one single factor. All right? However, did you see this e to the negative s, e to the negative 2s? Okay, I'm going to express this as a difference of squares. E to the negative s squared and 1 minus e to the negative s over s. Okay? Do you guys agree that in the denominator we have a difference of squares? That is 1 over 1 minus e to the negative s times 1 plus e to the negative s times 1 minus e to the negative s over s. Okay? So guys, essentially we're done here, all right? But I'm gonna go the extra few miles. Okay? Check. Cancel these two. This is s times 1 plus e to the negative s. Okay? And it seems like even more simplified, right? However, I'm gonna go for the extra miles and make it look fancy. I'm gonna make this look like a hyperbolic function. But what's the trick here? The trick here, party trick here is to multiply numerator and denominator by e to the s square, s over 2. I know that came out of nowhere, right? But there is a reason why I'm doing s over 2 and not just s. If I do just s, I would end up with e to the s plus e to the negative s plus s. That's just one. That doesn't actually spawn a hyperbolic function. This will, okay? This will do. How? Check this out. So this is e to the s over 2 divided by s times e to the s over 2. What is negative s plus s over 2? Isn't that plus e to the negative s over 2? Doesn't that kind of look like a hyperbolic function already? But not yet. We wished we had, check this out. We wished we had division by 2, right? To have a complete hyperbolic function, we can make our wish come true. Just do it. Just divide it. Provide it. Multiply. Okay? And guys, here is our hyperbolic function. Okay? This is our hyperbolic function here. E to the s over 2 over 2s. What is that? Cosh, right? Cosh of s over 2. All right? We're not done yet. We're not done yet. Hold on. Wait. This is equal to 1 over 2s. I'm going to move this cosh to the numerator as sich. We're not done yet. Just need to box our final answer.